Okay, hello everybody. My name is Shikib Mehri, and today I'm excited to present on our interactive evaluation of dialogue track at DSTC9. This track was co-organized with Yulan Feng, Carla Gordon, Seyed Hossein Alavi, David Traum, and Maxine Eskenazi. The goal of dialogue systems research is to develop dialogue systems that can have a back and forth conversation with a real user and strive for user satisfaction. And I really want to emphasize this last bullet point here. When we develop dialogue systems, it's important to consider the goal of the user and ensure that we develop the system such that we can effectively satisfy the goals of the user. Despite the fact that the fundamental goal of dialogue systems research is to develop systems that can eventually interact with real users, the majority of research thus far has focused on response generation on static datasets. And this essentially reduces dialogue to an input to output mapping. While this formulation is very convenient for developing neural models, it unfortunately neglects several important properties of dialogue. For example, long-term planning, error recovery, and user modeling and adaptation. These qualities, as well as many more, can't be effectively assessed if we're only trying to generate a response for a fixed context. And this is the type of thing that we really need interactive evaluation for. Furthermore, as we've seen recently, state-of-the-art dialogue systems are starting to achieve human-level performance on response generation. When looking at responses generated by Mina, we find that they are often more interesting, more engaging, more relevant than responses generated by humans. However, if instead we have Mina interact with real humans and we look at the resulting dialogues and assess their quality, we find that humans still far outperform Mina. Going back to the second slide that I had, I want to touch again on this third bullet point. Something that's important here is that the distinction between real users and paid users. Paid workers perform differently than real users, and this is because their fundamental goals are different. Paid users are doing a task, they're interacting with a dialogue system because they want to be paid. Real users, on the other hand, are interacting with the system because they want to interact with the system. And you really need a user to be interacting with the system of their own volition to estimate user satisfaction. So why are we as a community not doing interactive if it is so important and if it is so fundamental to dialogue systems research? Well, it's hard to collect dialogues in interactive settings. This requires a lot of infrastructure, and this might be too complex. It's also hard to collect dialogues with real users. Where are you going to get real users? How are you going to incentivize them to interact with your system? It's hard to evaluate the collected dialogues. Let's say that you solve the first two problems. What do you do with the resulting dialogues? How do you effectively evaluate them? And then, of course, it's expensive. Through our DSTC9 track, we hope to dispel some of these concerns and demonstrate both the feasibility and the value of interactive evaluation of dialogue. So our track consisted of two subtasks. First of all, we had response generation on the topical chat corpus. For the first subtask, we had ongoing automatic and human evaluation throughout the challenge. We also had a subtask for interactive evaluation. And interactive evaluation was carried out with real users on the Dialport platform. And again, we had ongoing automatic and human evaluation throughout the challenge. So let's start by describing the first subtask. The submissions were allowed to be trained on any datasets and use any available pre-trained models. We then took these submissions and evaluated them on the topical chat, frequent validation, or test set, depending on whether it was the final submission. We evaluated with both automatic evaluation, which included metrics like Meteor, BERT score, and user, and we also performed human evaluation on Amazon Mechanical Turk. So BERT score is a metric where you compare a generated response to a ground truth response using the embeddings generated by BERT. User, on the other hand, is an unsupervised, reference-free evaluation metric that measures multiple qualities of dialogue by adapting pre-trained language models with specific objectives. User is open sourced, and we release our human annotations to facilitate the development of other metrics. The idea behind user is that we have these 5 different dialogue qualities: understandable, natural, maintains context, interesting, and uses knowledge. And we construct pre-training objectives that aim to act as a proxy for these different dialogue qualities. Mass language modeling, for example, aims to estimate whether a generated response is understandable or whether it is natural. Once we have scores for each one of these qualities produced by the models that were trained with the pre-training objectives, we combine them with the regression to get an overall quality. And something that I want to show here is the correlations of a number of different automatic metrics on the topical chat corpus. And the results of this correlation motivated the 3 different automatic metrics that we chose to use throughout this challenge. If we look at the 3 best performing metrics, we see Meteor, which is a word overlap metric, performs reasonably, as does BERT score, which is an embedding-based metric. And then User, which is a reference-free metric that doesn't compare to ground truth response, has a strong correlation of higher than 0.4. We also note that User performs very well on the persona chat corpus as well. For the for the human evaluation for the first subtask, we annotate the generated responses for several different dialogue qualities, including things like interesting, engaging, relevant, fluent, and so on. These qualities, this list of qualities was decided by looking through the literature and constructing as exhaustive as a set of dialogue qualities as we could. This is what our annotation interface looks like. Essentially, we would show on the left, we would show the dialogue context and then the response generated by the system. Then we would have an Amazon Mechanical Turk worker answer several different questions about the response. Each one of these questions has thorough definitions and examples for each one of the possible answers that a worker could give. So for example, for fluent, since the available answers are no, somewhat, and yes, we have examples for what would be a no for fluent, what would be a somewhat, and what would be a yes. And we constructed the examples and the instructions by doing preliminary studies and ensuring that we got high inter-annotator agreement. And ultimately, with these instructions, we're able to get inter-annotator agreement of between 0.7 and 0.9. We also made sure to pay well to get dedicated workers because we really care about getting quality responses to these hits. So because we were running ongoing automatic and human evaluation, throughout the challenge, the submissions were ranked on a leaderboard, and the participants could look at the scores, understand whether one version of their system was doing better than another, and get a sense of how they stacked up against the competition. And we believe that this automatic evaluation and human evaluation was a valuable resource for the participants and really helped them during the development and validation process. For the final submission, we received 33 submissions, and we found that many submissions outperformed our baseline models, which were a transformer and a dialogue GPT baseline. We noticed across the submissions that almost all the submissions relied on pre-trained models, and the top systems really focused on addressing the one-to-many problem in dialogue during training, for example, through a 2-step training process. One thing that was really interesting was that many submissions opted not to use the topical chat training data whatsoever, and instead, through pre-training on large amounts of data, they were able to generate responses that may not have been in the style of the topical chat corpus, but were still preferred by human evaluators. And finally, here are the results of the first subtask. The top systems were very close in performance, but they still outperformed many of the other systems. We note that the automatic metrics correlated poorly at the system level, with Meteor and BERT score having Spearman correlations with human judgment of 0.23, and user having a slightly higher correlation of 0.35. One reason for this correlation is because these metrics are biased towards generated responses that are in the style of the topical chat corpus. What I mean by this is Meteor and BERT score do direct comparisons between a generated response and a ground truth response, meaning that if you follow the style and the wording of the generated response, the score is going to be higher. While user is unreferenced, it is still pre-trained on the topical chat corpus in a self-supervised manner, which means that it is naturally going to prefer responses that are in the style of the topical chat corpus. Since many of these submissions did not train on the topical chat corpus, the automatic metrics will punish these systems unfairly. On the other hand, human evaluation will rank a response fairly regardless of whether it's trained on the topical chat corpus. For the interactive evaluation subtask, again, submissions were allowed to train on any datasets and use any available pre-trained models. Once we received a submission, we collected dialogues for the submission on Dialport with real users. To attract real users, we recruited them through Facebook advertising. The users, in addition to being able to interact with the system, can provide feedback to the systems while they're interacting. After we collected the dialogues, we performed post hoc assessment through both automatic metrics and human evaluation on Amazon Mechanical Turk. Here's the Dialport interface. Dialport is an NSF-funded project with the objective of allowing the dialogue research community to get interactive dialogues with real users. We recruited users to interact with the systems by advertising on Facebook with broad targeting to English-speaking adults. Over the course of the challenge, we aim to collect at least 100 conversations per submission, and for the final evaluation, we collected over 200 dialogues for each system. On the right, we show the ad that we used. And you can see at the bottom that it received a lot of engagement with a lot of likes, comments, and shares. And our marketing strategies were not particularly sophisticated, which really goes to show that because we were able to achieve good engagement despite this, users really do want to interact with state-of-the-art dialogue systems, and it isn't really too much of a problem to attract users to this type of task. For the post hoc assessment, once dialogues were collected for each system, we performed post hoc assessment through automatic metrics, the Fed metric, and human evaluation on Amazon Mechanical Turk. We performed automatic evaluation with the Fed metric. Fed is an unsupervised, fine-grained evaluation metric that measures multiple qualities of dialogue, 18 to be specific, without any supervision using the Dialog GPT model. We released the Fed dataset as well as the Fed metric on GitHub. The way that Fed works is we use Dialog GPT to predict the likelihood of follow-up utterances. So what I mean by this is that given a dialogue history, like let's say, for example, the last system response was, did you know that cats sleep for 18 hours a day? We compute the likelihood that the Dialog GPT model would respond positively and the likelihood that it would respond negatively. So how likely is it that the Dialog GPT model would respond with cool, very relevant, versus that's not relevant? By taking a difference of these scores, we get a sense of how relevant this response might be. The Fed metric is based on the intuition that pre-trained response generation models have implicitly learned to capture some notion of dialogue quality and can tailor their generated responses to account for this. Through this approach, we measure 18 different dialogue qualities without any supervision. To the best of our knowledge, Fed is the only metric that can work for automatic evaluation in an interactive setting. This is because Fed does not compare to ground truth response, and then Fed does not need any training whatsoever. Whereas something like user, for example, even though it is reference free, does rely on self-supervised training and would not work in an interactive setting because the responses and the dialogues are not grounded in a data set. So the Fed metric, we construct 0 to 4 positive and negative follow-up utterances for each one of the 18 qualities. For example, for interesting, one of our positive follow-up utterances was, wow, that's so interesting, versus one of our negative follow-up utterances was, that's really boring. To get an overall impression score, we take an average of all the fine-grained scores. Through this, we achieved an overall dialogue level correlation with humans of 0.44 and correlations between 0.25 and 0.52 for the various fine-grained qualities. For the human evaluation on the interactive subtask, again, we had an exhaustive list of dialogue qualities that was constructed by looking through the literature and just taking a look at anything people had used to assess overall dialogues. And again, the instructions for these were very thorough, and the instructions were iterated on through preliminary studies until we got good agreement between annotators. So for the final evaluation on the interactive subtask, we received 11 submissions, and after removing offensive dialogues, we received a total of 5,682 total dialogues, with 2,962 being at least 4 turns. And what I mean by removing offensive dialogues was that we took a look at the dialogues, and because these are real users, sometimes they might say things that are offensive or say things that we don't necessarily want to use for evaluation. So what we did was we took any dialogues that had any curse words in them and we removed them. And we had to remove somewhere between 40 and 50% of dialogues, which left us with 5,682 total dialogues. We had 41,640 total dialogue turns, and the dialogues were collected over 3 days through Facebook advertisements with a total cost of $2,500 for all of the advertising. So this evens out to about 86 cents per dialogue. And this really, these results really demonstrate that it's not expensive to do interactive evaluation, and it is very feasible to do this type of study. And we got good dialogues with the average number of turns being 8.95 in our resulting data set. We also note that we received a lot of feedback from real users. So on the dialport interface, we have these buttons, and if you look at the buttons, you can either like a response, you can dislike a response, you can provide written feedback, or you can correct the generated response. In total, we received 3,829 total pieces of feedback, with the majority of those being likes and dislikes. Although we did receive a large number of system corrections and written feedback as well. And the feedback overall was fairly high quality. For example, on the right here, we show that some of the feedback includes things like, the system forgot I was single shortly after asking about it. The system talks about pizza too much. This one isn't even having a conversation with me. Is it just pulling vaguely relevant quotes from Reddit or something? And this feedback was provided to the system developers throughout the challenge, and we believe that it acted as a valuable resource for developing their systems, iterating on their systems, and choosing between systems. So this goes to show that there is more value to interactive evaluation beyond just getting full dialogues. You can also get real feedback from real users. So here are the results of our interactive evaluation. First, let's discuss the performance of a couple of different metrics. First of all, we find that Fed has a system-level correlation with humans of 0.49, although it does accurately predict the top 2 best performing systems. Something that we found really interesting is that the average number of turns that occurred between a system and a user has a system level correlation with human judgments of 0.94. This means that if we look at how long users on average spoke to a particular dialogue system, it is a really strong predictor of the quality of the dialogue system. We see, for example, that the top two systems have a total average number of turns that is much higher than any of the other systems. And these two systems are also the highest ranked, both according to the human evaluation and the Fed metric. So again, this really demonstrates the value of doing interactive evaluation with real users. In general, across the interactive evaluation submissions, we notice several trends. All these submissions use pre-trained models. The two systems with stars here are our baseline models. Number 11 is our transformer model that was trained on the topical chat corpus and didn't use any pre-training. And number 6 is the Dialog GPT model. So we note that all the submissions above 11 use pre-training and they significantly outperform the transformer model. Something else that was interesting is that the top systems are not end-to-end models, are not completely end-to-end, and they instead use pipeline architectures, for example, doing generation and then maybe ranking and then post-processing, or having a model that chooses between responses by looking at the coherence or something like that. So let's look at a couple of example dialogues. In this one, we see that the user is describing that they run a construction company and the system is generating engaging responses and they're having a very cohesive dialogue. This dialogue was particularly interesting to me. Here what's going on is that the real user is testing the system by simultaneously carrying out two threads of dialogue. What's happening here is the system asks the user what they're up to, and the user responds to with "I'm playing video games." And when the system carries on the conversation, and at some point the user says, "I'm playing League of Legends." When the system responds to this, the user starts talking about classical music. And then when the system responds to this, the user goes back to the first thread of dialogue and responds to the question about League of Legends. And this continues. And this really shows that the real user is striving to push the boundaries of the system and really test its knowledge. But furthermore, this shows that the system is performing very well. It's able to deal with this testing from the user, and it's displaying strong domain-specific knowledge about both classical music and video games. So to conclude, on interactive evaluation, we demonstrated that interactive evaluation is feasible. On Dialport, we're able to collect a good dialogue with a real user for less than $1. However, Dialog is a completely free resource for the Dialog community. So if you're interested in doing interactive evaluation with real users, feel free to get in touch with us, and we're more than happy to collect real interactive dialogues with real users for you. We also note that interactive evaluation with real users is important. The differences between the systems are much more pronounced in the second subtask than in the first subtask, just because interactive evaluation is more challenging. With interactive evaluation, we also see that the number of turns or the conversation length is a strong predictor of the quality of a dialogue system according to humans. Something else that's interesting is that real users provide feedback very frequently, which is a valuable resource to system developers. On open domain dialogue systems, we find that pre-trained models are vital, and it's valuable to go beyond end-to-end and build pipelines which result in better coherence and relevance. Something that is also interesting is that fine-tuning is not always necessary. Automatic metrics overstate the importance of fine-tuning, as we saw with both Meteor, BERT score, and the user metric. And with automatic evaluation, we found that automatic evaluation has lots of room for improvement. Reference-free metrics, for example, user and Fed rather than Meteor and BERT score, correlate slightly better with human judgment, but again, there's lots of room for improvement. And because we provided these metrics throughout the challenge, they were valuable as a tool during development. Average conversation length in interactive settings is a strong predictor of human judgments. Thank you, and I'll be happy to take any questions now. Okay, if there are no questions, then we can move on to the next talk, which is by WeChat AI.
Okay, we should wait till the scheduled time. Probably it's in 10 more minutes. By the way, thank you, Shikib, for the great talk. So actually, your track touches on. So I don't know if you attended the panel discussion yesterday, but it kind of it was mentioned in like many panelists called out on this track actually for doing interactive evaluation, and this is something which has been missing in like the dialogue research community, especially with metric-based optimization. Uh, Yeah, and also like it was in all the tracks we have had, basically we release data and then we have a submission deadline, and in the end, like kind of participants submit their entries. But here, as you said, it was an ongoing process. So like it was not just like one-time interaction with the participants, but generally participants, like there is a continuous interaction and learning and sharing of feedback with the participants.
Right, yeah.
So go on. Yeah.
Oh, sorry. I was just gonna say, yeah, like I agree with a lot of what the panelists said yesterday. This type of track is it is starting to become a lot more required in the dialogue community, and I hope that more people start looking towards interactive evaluation for maybe like future iterations of DSTC.
So I had like a question about from organizational standpoint, was it like a lot of work for you?
Yeah, for sure. I think it was a lot of work because we did have to, for example, because like okay, for example, whenever participants would submit systems for the interactive evaluation, we had to make sure that it was running on a server, that it was available as an API, that we could interface with that, and then make sure that we could get real users, keep the entire system up for as long as we needed until we got the dialogues. And then once we got the dialogues, we then had to perform we had to like create an mturk hit every single time. So there was a lot of manual processes there that made it difficult, but possibly with time, a lot of these things could be automated.
And were the participants, were they required to submit like a binary, or were they hosting their own
Yeah, so
system?
the way we set it up was, well, because we didn't want to run the models ourselves, the way we set it up was that they would that we have like this wrapper that will turn a model into an API. They would run that on a server and they would give us the link so that we can make requests to that API endpoint.
I see. And I was also curious, like since most of these users you recruited on Facebook, so are all of them paid users, or
No,
like
no, 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 no.
for?
So when we recruited users on Facebook, the way our ad worked was just like, here's some nice dialogue systems, come and interact with them. The users were not paid at all. They just talk to the system because they want to talk to the system. And that's a real distinguishing factor here, because when they want to talk to the system, rather than talking to it because they get paid, we observe things like they talk to systems longer if the systems are better.
So like I was wondering how we like how did you prompt the users to start a conversation? Like was it just talk about anything, or were they kind of primed into talking about certain topics?
No, it was completely open domain. So essentially, this is the slide that that shows the interface that the user saw. Welcome to Dialport. You'll be matched with a random conversational AI. Feel free to chat about anything. please provide feedback to help assess and improve these systems. So they could talk about anything, and then our ad was just like, are you bored? COVID-19 got you down. Come talk to our chatbots. So not primed at all, not paid. They just talk to the systems because they wanted to.
Are there any questions from audience at this point? I think Chori has a question. Yeah.
Can I?
Yeah, sure.
Okay, so thank you very much. Nice talk. Actually, this evaluation is very expensive and people want to do it, but normally we cannot do it. And one thing I would like to, extend this activity to get the consistent evaluation metrics from this real time, evaluation. If you can, make the evaluation, objective evaluation metrics based on the human judgment, objective metrics, and this real time, real time dialogue evaluation result will be combined together. Can you make a much nicer, stable dialogue evaluation for
Okay, so
in a cheaper manner? Yeah.
To clarify, you're asking whether we can combine some of the human evaluation with the automatic metrics?
Actually, the result of you obtained. So real-time evaluation result. So means that we have a kind of numbers, correlation between the result. So means that we can find another, higher level metrics to observe, the, task. So in your case, you rely on the one, each dialogue system, but, the task is defined. So everybody wants to improve the performance, and objective evaluation and human judgment is a standard evaluation for dialogue system right now. And you try to introduce the, real-time dialogue evaluation by humans. So can we introduce this result? You have the numbers. So as normalize the evaluation metrics for the current evaluation. So I would like to have a bonus from your research result.
Okay, so if I understood correctly, essentially what you're saying is that, like, we have the automatic evaluation for all of these, we have the human evaluation. Can we sort of like rebalance the automatic evaluation based on the human evaluation performance?
Yes.
Yeah, that's an interesting point. I think that would be feasible. I think like although like to be honest, my take on automatic metrics, well, first of all, they might not be there's so many problems with automatic metrics beyond that. But then a lot of people compare relatively with automatic metrics, like is A better than B versus looking at the absolute difference between the scores. That type of thing could definitely be useful, just to make the absolute differences between two scores more meaningful. But I think that there's like so many problems there that this might be like jumping the gun a little bit.
Yeah, so, but we talk about the accuracy or blue 0.1 difference, blue difference.
Yeah.
What's the meaning of, that numbers?
Right.
If you know the meaning of the numbers based on a human judgment, actually we can, okay, if in this task, if we have the difference of 0.1 blue score, it means humans can sense, recognize the difference. Like,
I see. Yeah.
So human sensitivity for the dialogue system needs to be defined by human scores. Actually, objective scores should be normalized by human scores. If you can,
that's a really interesting idea. Yeah, I think we'll definitely look into something like that and see how feasible it is.
Yeah, thank you very much.
You-
Anyway,
Thanks for your comment.
Yeah.
Even like if you release the data set of these conversations with the associated scores so
Yeah.
that other people can train such a metric,
Right.
that would also be a valuable resource.
Right. Yeah, of course. We definitely plan on doing that. And we have released several data sets like that with those fine-grained annotations. Both the user data set and the fed data set have dialogues and then the corresponding annotations. Okay, so I believe it's time for the next talk now, and the next talk is from WeChat AI, who tied for first on the first subtask and placed third on the second subtask.
Okay, can you hear me? I will
Yes.
share my screen. Okay, I will begin. Hello, everyone. I'm Zekang Li from Institute of Computing Technology, Chinese Academy of Sciences, and WeChat AI. I'm excited to introduce our work in the interactive dialogue evaluation track at the DSTC9. On behalf of my colleagues, Zongjia, Jinchao, Feng, and Zhou. This is the content of today's presentation. First, I will introduce a task description containing static dialogue evaluation and the interactive dialogue evaluation. Then I will briefly introduce our approaches, experiments, analysis, and some further work we did after a challenge for the two subtasks. Now, let's begin. Subtask 1 is the static evaluation of dialogue. This task is to generate responses given the dialogue history and the related knowledge. Here is an example from the topic chat dataset. Given the knowledge and dialogue history, we hope our model can generate coherent and informative responses. Subtask 2 is to build an interactive chatbot to chat with human effectively. The figure is an example of human-bot conversation. Here is the subtask 1. This is a model architecture for subtask 1, generally a GPT-2 model. As shown in the figure, in the training stage, we concatenate the related knowledge and the context as the input, and predict the response using negative log likelihood loss. We fine-tune the GPT-large on the topical chat dataset. In the generation stage, there are various decoding methods. We try two cancel decoding methods, beam search and the sampling-based methods. Beam search always generates general responses like, I don't know, I'm not sure that. There are also repetitions in the responses generated by the beam search. Sampling-based methods can generate more fluent and diverse responses. However, the sampling-based methods always miss some important information in some ways. So we propose a simple but effective response in sample method. First, we have n response candidates generated by top K or nuclear sampling. Then we select a metric such as meter, birth score, or blue. We initialize the score for each response. For each response, we calculate a metric between the response and the other candidates. We select the response with max score in the last step. Here, we present some responses generated by nuclear sampling with p equal 0.9. Compared to the ground truth, example 1 to 5 means different information. For example, example 1, the response means the time information, 1975, and the example 3 means the name of the basketball team. By choosing the response with the proposed response ensemble method, we can select the most appropriate informative responses that achieves max score with the ground truth. Here is the experimental results for subtask 1 static dialogue evaluation. Containing automatic evaluation, containing this automatic evaluation and the human evaluation. Our 3 different submissions get different performances on the 4 metrics. The asterisk denotes that it ranks or tie first over all submissions into competition. Our model with birth score ensemble gets the highest birth score, and with meteor ensemble gets the highest meteor score, which shows that our response ensemble method can effectively improve the performance. We also try to use the system from the subtask 2 for the subtask 1. Note that we don't use knowledge in the subtask 2 system. The responses from the system tied first according to the human ratings, but it performed poor on the meteor birth score and the USR. We discussed the reason of the big gap between human ratings and other automatic scores. First, the knowledge text is selected according to the gold response. Second, the conversations may be too topic related, and the human judges may not familiar with the topic, so the human ratings may be not accurate. We found some examples that human judges gave 3, a moderate score, to the responses which are almost the same with the ground truth. Third, human judges may prefer coherent and fluent responses more than informative responses. So the knowledge seems not such important. Next, I will introduce our approach for subtask 2. This is our overall system for the subtask 2, which contains 4 modules: pre-process, dialogue module, score module, and the post-process. In the pre-process, we construct augmented conversational data to handle various situations such as topic changing, which is usual in the real human-bot conversations, but infrequent in the collected human-human conversational data. In the dialogue module, we design a dialogue planning model and employ the pre-trained Plato 2 model to generate response candidates. In the score model, we utilize dialogue RPT, Plato 2, and the natural language inference model, abusive detection model to select the most suitable response. In the post-process, we reformat the responses to make them more human-like. Next, I will introduce this method, these modules in detail. Here's the detailed augmentation process. First, given a dialogue A, then we randomly drop some utterances from the end and get a new dialogue C. And then we randomly select another dialogue B. We concatenate the dialogue C and dialogue B as a dialogue D. We randomly do the augmentation according to a fixed probability. The data augmentation effectively handles the situation when user change topics suddenly based on our observation. Dialogue model contains the dialogue planning model and the pre-trained plot model. Dialogue planning model aims to capture the whole conversation dynamics and predicts feature to get the response generation. There are about 900 million parameters in the model. Plato 2 is a large-scale pre-trained dialogue generation model with discrete latent variables. The parameter size of Plato is about 1.6 billion. I will introduce our dialogue planning model in the following. In the real human-human conversations, dialogues about the similar topics should have similar conversational dynamics. And the humans always consider the influence of their next utterance before they continue the conversation. We hope to model the conversational dynamics and predict the future development of the dialogue so that the model can generate responses with the guidance of the predict feature. Before we introduce the dialogue planning model, we first define some terms. CK, the gray dotted line, denotes the dense representation of the dialogue history at the case utterance. We also named it as a context. IK, the pink solid line, denotes the semantic influence brought out by the case utterance, which can be regarded as the difference between CK and CK+1. The dialogue planning model aims to capture the context dynamics. In figure, it's the changing process of the gray dotted line, and predicts the future semantic influence, the pink solid line. Here's the architecture of dialogue planning model. The dialogue planning model mainly consists of input embeddings, transformer blocks, and the flow model and the response generator. A transformer block consists of layer normalization, multi-head attention, and feature-forward layers. We employ the pre-normalization used in GPT-2. We keep the unidirectional encoding in the transformer blocks. We can obtain the history context CK encoded by transformer blocks at the position of the spectral token C. The flow model is also a unidirectional transformer block, which predicts the context using all previous contexts and capture the context dynamics. Response generator is used to generate responses with guidance of the predict semantic influence IK brought out by the response. We designed 3 training objectives to optimize the dialogue planning model. First, context flow modeling. We predict the next context based on all previous contexts using mean square loss. Second, semantic influence modeling. To measure the predicted influence brought out by the utterance, we design a backwards loss directly using the predicted future IK. Third, response generation modeling. Dialogue planning model generates responses with the guidance of the predict semantic influence. We use the negative log likelihood loss. In the training, we initialize parts of the dialogue planning model with GPT-2 large and fine-tune it on the topical chat dataset and the BST dataset. Score model contains the following 4 modules. First, given 20 response candidates, we use abusive detection model to filter out the responses with abusive words. And then we use the scoring model in Plot2 to choose 10 most appropriate responses. And then we use natural language inference model to filter out the responses that are contradictory with the dialogue history. And last, we use the Dialog RPT, a large-scale pre-trained response ranking model based on the human feedback, to select both the best response that human likes. Here's the experimental results. Our system significantly outperforms both baselines, transformer and dialog GPT, and ranks the 3rd in the final human evaluation. After the challenge, we did some further explorations. We first pre-trained the dialogue planning model on the large-scale Reddit comments. By training on the large-scale dataset, the dialogue planning model can capture the expectation of the dialogue development. As shown in the figure, there are several potential responses for a context like the green points. dialogue planning model can learn the expectation of all potential responses and capture the dialogue template. If the utterance is not appropriate like this, like swimming, like the red point, the similarity between the red point and the expectation is low. As the dataset contains human-human conversations, the similarity between the real utterance and the expectation can be regarded as the human likeness of the real utterance. Based on the consideration, we propose the flow score, an automatic reference-free metric for interactive dialogue evaluation. Flow score measures the cosine similarity and the length similarity between the predicted semantic influence and the real semantic influence for each utterance. We scale the similarity to 1 to 0. Then the overall flow score for a dialogue is computed like the perplexity. We calculated flow score on the human bot conversations collected from the 11 chatbots in the challenge. B1 to B11 denotes the 11 different chatbots in the computation. As the human-human, also as the human conversations are always regarded to be better than human bot conversations. To explore the flow scores performance on the real human-human conversations, we also randomly sample some human-human conversations from the BST dataset, which is denoted as a human in the columns. We assign the human ratings for the human-human conversations is 5.000. The flow scores are shown in the first table. We also compute the Pearson correlation and the Spearman correlation between the flow scores and the human ratings. The flow score shows impressively high correlation with the human ratings. The correlation coefficient is about 0.9. This figure shows the 2D TSNE visualization of the semantic context of human bot conversation encoded by our pre-trained dialogue planning model. The conversation can be split to 4 topics. From 1 to 4 is about greetings, and then about talking about wideband day, and then explaining the terrible experience seeing the doctor, and the last discussing something about swimming. Correspondingly, in the visualization, the semantic context flow visualization changes a lot when the topic switches, like this to this here, and then here, and then here. Revealing that the dialogue planning model can capture the conversation dynamics in the dialogue and effectively measure the semantic influence brought out by each utterance. Besides, it seems like different speakers keep their own context flows. Like this is the odd number and this is the even number. Okay, thanks for your attention. Thanks to the organizers. Any questions?
Thanks for the great talk. I had a couple of questions. So what did you do the flow and fed comparison on? Did you collect a data set or did you use an existing data set?
In the challenge, we don't use the data set, the data we collected, but in the in our further work, we use the we use the data collected from the dialogue port to evaluate the flow score. Okay,
yeah, that's very cool. It's very impressive to have such a strong correlation with human judgments. And was this just so to clarify, you collected an additional data set of interactive dialogues, and then you added in some human dialogues in there. You got human judgments, and then you computed the correlation of both metrics.
Yeah.
Okay, cool. I had another question about so in your subtask 2 submission, you had a scoring module, right? And this module was like consisted of dialogue RPT and NLI and this stuff. And what I was curious about was whether you think that it is possible to, rather than having these as a 2-step process where you first generate a number of responses and then rank them, whether you could incorporate the score model as maybe like use reinforcement learning with a loss that just like trains the model directly to generate responses that would get a high score.
Yeah, I think using reinforcement learning will be a good idea. It can be optimized directly from the human feedback. Okay, but it's too cost effect. It's too cost.
Okay, cool. Makes a lot of sense. Okay, any other questions? I have one other question. At some point you mentioned that you had, after the score model, you had some post-processing.
Yeah.
What exactly is entailed in that post-processing?
The process is mainly we use post process to reformat the response to make them more human-like. We change the first words of the response to uppercase and change some the entities like the for example the New York City is the uppercase. We mainly reformat this.
Okay, I see. And for all of these things, did you do any ablation studies to see how much they would impact the performance?
Yeah, we in the challenge we submitted several systems and we see some improvements. Yeah.
Okay, so real users do care that the responses has proper
Yeah,
capitalization. Okay.
In the human charge, we think so.
Okay, that's very interesting. Any other questions from the audience?
I'm wondering what happens if like such systems are kind of made to interact with themselves. So you create 2 instances of the same system, ask them to talk to each other.
Pardon, I can't understand what you are saying.
Oh, I mean, like this is a dialogue system, right? Like it can do conversation like a chit chat. So what would happen if like we make the system interact with itself? So we create 2 instances of the same system. Does it generate like any good dialogues, or is it like just going to be probably not sensible? It's a general question, not for your system.
Okay.
Shikib, have you tried such experiments?
Sorry, I can't follow it.
Not exactly. I haven't tried something like that, but I have tried getting open domain systems like Dialog GPT to talk to task-oriented systems, and that produces some interesting results. Surprisingly, they can carry out coherent dialogues. But with very sophisticated systems like this, I'm sure that it would be much better.
Interesting.
Okay, so our next talk is from Baidu, and they placed, they tied for first on the first subtask and then also placed first on the second subtask. And also the two example conversations that I use in my talk came from one of their systems. So I'm looking forward to hearing this talk.
Thanks for the introduction. Can you see my screen now?
Yes.
Good. Hi, everyone. I'm Siqi. Today, I will introduce our work submitted to Track 2 and Track 3, the Unified Pre-training Framework for Conversational AI. We know that the neural models in conversational AI can be roughly divided into 3 categories: the open domain chatbot, the knowledge-grounded dialogue agent, and the task-oriented dialogue systems. In the past, due to the significant difference among these tasks, it is usually necessary to customize the modeling and the training for each task. Recently, the pre-training language models have obtained great success in dialogue generation. However, there still lacks a unified pre-training framework which may effectively handle all these 3 conversation tasks. So in this work, we will explore the application of Plato 2 on these 3 tasks, including the open domain chit-chat, the knowledge-grounded dialogue, and end-to-end task-oriented conversation. In fact, Plato 2 was initially designed as an open domain chatbot. We know that there is a one-to-many mapping relationship in open domain conversations. It means that the dialogue context might have multiple appropriate responses. Here in this example, we have the dialogue context, it is snowing outside. Then we can have this response. How about making a snowman? It is appropriate. We can also have another response like this. It is so cold, I really miss summer. Both responses are appropriate towards the context. For the conventional dialogue generation models, they are trying to fit the one-to-one mapping relationship between the dialogue context and these multiple responses. They may generate some general and dual responses during inference, like that is nice. Well, to tackle this one-to-many mapping problem, Plato 2 encodes a discrete latent variable into the network for diverse response generation, and Plato 2 is trained with 2-stage curriculum learning. And here is the overview of Plato 2. In the first stage, and the simplified one-to-one mapping modeling, a coarse-grained generation model is trained for general response generation. This model will capture the typical patterns of response generation. Sometimes it may result in general and dual responses. Despite the problem of safe response, this model is still highly effective in learning the general concepts of response generation. And the curriculum learning continues to the second stage, which contains the training of a fine-grained generation model and an evaluation model. The fine-grained generation model encodes the discrete latent variable for diverse response generation. Here, this latent variable, Z, is one k-way categorical variable with each value corresponding to a particular latent speech act in the response. This model will first estimate the distribution of this latent variable, and then it will generate the response with this sampled latent variable. Here, these 2 tasks, they will share the network parameters. And we also use the Gumbel softmax to make sure the gradient is differentiable in the sampling operation. And to select the most appropriate response, an evaluation model is trained to estimate the bidirectional coherence between the dialogue context and response. This model will help select the most appropriate response from these multiple candidates. During inference, there are two steps to produce this final response. Here we have this context, how is their vacation? And firstly, conditioned on each latent value, the model is able to generate multiple diverse responses like this. And then the evaluation model will perform ranking and select the one with highest coherence score as a final response. Here, the final response is amazing. I had a wonderful trip to Hawaii. Besides the open domain conversation, Plato 2 is also can be also applied to the knowledge grounded dialogue. Similar to the open domain conversation, the one-to-many mapping relationship also exists in the knowledge grounded dialogue. Given a dialogue context, multiple pieces of knowledge might be applicable for the response generation. Here is one example of knowledge grounded dialogue from persona chat. In this example, two partners, they are trying to know more about each other by discussing their persona profiles. After greetings, in this response, we can talk about the information of children or games of thrones or some other information in the persona profiles. It means that we can generate multiple diverse responses using different background knowledge. For knowledge grounded dialogue, the background knowledge can be encoded directly into the Plato 2 framework by adding a segment of knowledge before the dialogue context. Based on the background knowledge, the dialogue context, and the latent variable, the fine-grained generation model is able to produce diverse knowledge-grounded responses. And the evaluation model will consider the coherence with the dialogue context and the consistency with the background knowledge to select the most appropriate response. And Plato 2 can be applied to task-oriented conversation as well. Here, distinct with the open domain conversation and knowledge-grounded dialogue, the task-oriented conversation is supposed to accomplish a particular goal. Therefore, the semantic mapping between the dialogue context and the response will become less diverse. To this end, the one-to-one mapping generation model in the first stage will be used for the task-oriented conversation. Well, even with this powerful pre-trained generation model, it is still challenging to carry out end-to-end task completion conversations. As such, several techniques are employed in our work. In task-oriented conversations, the generation model needs to interact with its external database. So for the effective interaction with external database, our model will first generate the dialogue state. It will be used as a constraint for database query. Then the system action can be refreshed according to the query results. Based on the dialogue state and system action, the model can generate the system response. Secondly, it is crucial for task completion to extract the precise entity from the conversation. To this end, the further matching between the dialogue context and the database is carried out to identify candidate entities for enhanced entity representation. Thirdly, to deal with these ambiguous user requests, active clarification is introduced by raising one more question towards the user. For example, given the user utterance, I want to find a hotel to stay. It is hard to tell whether the user wants to find a place to stay or the user wants to find a hotel instead of a guest house to stay. So in this case, the system will further ask, would you like a guest house or hotel for clarification? These techniques help our model achieve a better success rate and improve the user experience in the task-oriented conversation. And for the comprehensive evaluation of Plato 2, we have enrolled in multiple tasks of DSTC9, including the track 3, task 2, the interactive evaluation of open domain conversation, the track 3, task 2, the static evaluation of knowledge-grounded dialogue, and track 2, task 1, the end-to-end task-oriented conversation. In the experiments, we leverage the large-scale pre-trained models of Plato 2 for these 3 tasks. Plato 2 is a dialogue pre-training model trained with 684 million samples extracted from Reddit. There are 1.6 billion network parameters in it. We know that the interactive open domain conversation is the most challenging direction in dialogue systems. The user can talk about any topic, and the system's reply needs to meet a high standard on many aspects, including the coherence, consistency, informativeness, engageness, and so on. In DSTC9 track 3 task 2, real internet users are attracted through Facebook advertising, and they will communicate with the backend dialogue systems through their port. Then these collected logs will be distributed to the AMT workers for further assessments. From this table, we can see that Plato 2 achieves the highest score of overall human rating and performs well on many evaluation metrics, like the diversity, topic depth, understanding, and so on. For the knowledge-grounded dialogue, the experiments are carried out on topical chat. There are 3 entities in topical chat. Each entity is associated with several short facts or articles. In the experiments, for each conversational turn, there are several facts available, and the system can leverage these facts for response generation. Well, as large-scale pre-trained models are able to pack the knowledge into the network parameters, as such, we test 2 experimental settings. The first one is Plato 2 with explicit knowledge. In this setting, the given knowledge are appended before the dialogue context, and the model learns the response generation based on explicit knowledge. The second experimental setting is Plato 2 without explicit knowledge. In this setting, the model tries to encode the knowledge into the network parameters implicitly and learns the response generation directly. Since the knowledge scale in topic chat is not that large, so for the Plato 2 without explicit knowledge, it can still pack the knowledge into the network parameters. From this table, we can see that there are 3 models tagged in the first place. The top 2 are our submitted Plato 2 without and with explicit knowledge. For the end-to-end task-oriented conversation, experiments are carried out on multi-words 2.1. Besides the automatic evaluation, the MTL workers are asked to talk with these systems for task completion. Here, from this table, we can see Plato 2 achieves the highest score on success rate with database grounding. This metric will evaluate whether the system's response is consistent with the backend database. And for this metric, success rate without database grounding, it will not consider the consistency between the system response and the backend database. And in the final ranking, the first 2 models are placed as a co-champion based on the average success rate. Here is one cherry-picked example for case analysis. This dialogue segment is selected from the interaction between the real user and our system. In the Dialport platform, users are informed in advance that they will talk with AI bots. Here, we can see the user size. In the office, I just have to use my brain. And the system answers, yeah, the office is oftentimes a stressful environment. And that's why I'm chatting with about right now. From in this conversation, the user and our system discuss about the job in the office, the robots, and efficiency. This example demonstrates the effectiveness of Plato 2 in generating the coherent and engaging responses in open domain conversation. Now we come to the conclusion part. In DSTC9, we have explored the application of Plato 2 on several conversation tasks. Plato 2, it is the dialogue pre-training model and is trained via two-stage curriculum learning. The one-to-one mapping model of the first stage can be applied to task-oriented conversation, and the one-to-many mapping models of the second stage are suitable for open domain conversation and knowledge-grounded dialogue. The comprehensive evaluations in DSTC9 verify the effectiveness of Plato 2 as a unified pre-training framework for conversational AI. Our pre-trained models and source code have been released at GitHub. Here is a link and the corresponding QR code. Feel free to scan it. Well, despite the effectiveness of Plato 2 on several conversation tasks, Plato 2 still suffers from several general limitations, including the factual error, the logic inconsistency, the toxic and biased language, and expensive inference. Recently, some pioneering works have been introduced to alleviate these problems. For example, the retrieval augmented generation employs the knowledge from Wikipedia to reduce these factual errors. And some recipes are explored and discussed to increase the safety in open domain chatbots. And for the inference latency, recently, we have explored several techniques like the operation fusion and model distillation for acceleration. And we have obtained the acceleration of 5 times. With this acceleration, we have deployed the Chinese version of Plato 2 into our products of the company. And we have received some very positive feedbacks from this product team. Yeah, our future work will be carried out along these directions to improve the model's performance. Yeah, that's all. Sorry, that's all. Thank you.
Thanks for the great talk. Are there any questions from the audience? I have one question. So if I understood correctly, for the interactive subtask, you essentially just use the outputs of Plato 2?
For the interactive, the rank 1 solution, you mean, right?
Yes.
Yeah, this is open source version.
Okay.
Yeah.
Okay, that's cool. One thing I'm curious about is why do you think that you performed better than the submission from the last talk that we heard? Because they use Plato 2 as well.
So I'm not sure. I noticed that they use Plato 2 in this task, knowledge grounded dialogue. Yeah, it seems that this is test Plato, right? I'm not sure. Maybe I need to check with Zekang. I'm not sure whether they use Plato in this open domain conversation or not. Yeah,
Okay.
so here we just see some DPKS something. Yeah.
Okay.
Since if they use
think they
Plato,
did.
we expect they can get similar results like this one, since this is just the open source version. Yeah.
Did you think at all about doing any post-processing, or did you have to do anything like that of the generated responses? Or did you find that the direct generated responses were good enough already?
For post-processing, we just remove those candidate responses with serious repetition with this context. So yeah, only this one.
So you generated multiple responses and then you just deleted the ones that had a lot of redundancy between the context? Okay.
Yeah, since this is the sampling-based methods, yeah, this is a conventional post-processing procedure to remove those. Yeah.
Okay, that's very interesting. Are there any other questions from the audience?
How does the system do in terms of the latency?
Latency, yeah. For this problem, well, for the Chinese model of Plato 2, here the latency, the average time for inference is about 1 second per sample. So for this open source implementation, so it takes about 1 second. Recently, we have explored several strategies, including this operation fusion. So we fuse all the operators of this transformer into one big OP. And with operation fusion, we have obtained the acceleration of two times. So we have reduced this inference latency to 0.5 second. This strategy will not hurt the performance. Another strategy that we have tried is this distillation. So the original Plato 2 has 32 transformer blocks. So we use it as a teacher model, and we use another smaller model of 12 transformer blocks. And we perform distillation between the teacher and the student model. The performance may drop a little, but it's still tolerable. And we have boosted the performance. We have boosted the QPIs further by around 2.5 times. So in this case, we have increased the query per second QPIs from 1 to 5. So with this acceleration, we can deploy this model on our products. Yeah.
So for the challenge submission, you submitted the original version, like without distillation. Right?
For this open domain conversation, we use this open source version. Yeah, this is open source version. For some other, like the knowledge grounded dialogue, we fine tune it on the topical chat, this compass. And similarly for the task oriented conversation, we fine tune the pre-trained model on multi-words 2.1. Yeah.
So I'm wondering if during interactive evaluation, any of the users complained about latency. Or if it is not a big issue, maybe we don't need to solve it.
It seems that human workers, since 1 to 2 seconds is still tolerable. Yeah, so we have deployed several services on our machine, so it's still okay for the human bot interaction. Yeah.
So to add to that answer, we did have some systems that submitted that were much slower than 1 second and would take longer. And we found that in those instances, users would often just like leave the website and stop talking to the systems. So they do maybe like 1 to 2 seconds is tolerable, but when you start approaching 5 or 10, it gets annoying. I had another question here about the knowledge grounded experiments. So here you found that Plato 2 without explicit knowledge performs better or on par with the Plato 2 with explicit knowledge. But in our track, we used like the topical chat corpus as both the frequent test set and the infrequent or the rare test set. So I'm wondering whether, oh yeah, and we only use the frequent test set. So the frequent test set is like knowledge that frequently appears in the training set, whereas the rare test set is like knowledge that appears less often. So I'm wondering whether you have carried out any experiments on the rare test set or whether you plan on doing that just to see whether this the same relationship exists.
Oh, we haven't. We haven't. We will in the near future. I think that might be the reason why the Plato 2 without explicit knowledge can obtain this performance. For those experiments on the not frequent conversations topics, I think the performance of this one might drop a little since this model has not seen that knowledge before, right? So the accuracy of knowledge may drop. And for this model, Plato 2 with explicit knowledge, I think it may keep the performance on that data set. Yeah.
Yeah, that would be interesting to see because like
Mhm.
it's I'm curious about how much knowledge is derived from pre-training already, like how much the model already knows without even training on the data set.
Yeah. So we have tried some other experiments on some other data sets, and we noticed that the factual error is really a major issue for pre-trained models. So so if we just pre-trained using the Reddit conversations, and it seems that sometimes the model does something that's very ridiculous. And recently we have tried to use this knowledge from Wikipedia or some other sources to help improve this performance to reduce these factual errors related to knowledge. Yeah.
Cool. Very cool. Thanks for the talk. I
Thank you.
believe it's time to move on to the invited talk.
Yeah. Thank you, Shikib, for and all the participants of track 3. It was a really interesting discussion.